Welcome to the Solar Oasis Challenge, where your brain is the only thing standing between a thirsty horse caravan and an endless supply of fresh water. Picture yourself in the middle of a shimmering desert, the sun blazing overhead, and you have just one parabolic trough collector mounted on your high-tech camel cart. This isn't any ordinary reality show. This is Desert Tech Stars, and you've made it to level 3, the mirror's secret. Your mission sounds simple. Set the tilt angle of that trough once, lock it in for the whole day, and collect as much sun power as possible to distill pure drinking water. Every single milliliter of water you produce earns you 1 precious point. But here's the catch. The sun moves, and your trough doesn't. Get the angle wrong, and you'll watch your points evaporate faster than a puddle at high noon. Today's arena is located exactly at the Tropic of Cancer, latitude 23.5 degrees north. The date, the summer solstice, when the sun's declination also sits at 23.5 degrees north. The sun will blaze a path that starts in the northeast, climbs to a point directly overhead at solar noon, and then dips into the northwest. Your collector is a parabolic mirror that stretches 2 meters long and 1 meter wide, designed to focus a constant direct normal irradiance of exactly 800 watts per square meter onto a thermal receiver. Assume the device converts a fixed fraction of that beam energy into distilled water, so maximizing total daily captured energy is equivalent to maximizing your score. You can tilt the aperture at any angle beta, measured from horizontal, where positive values mean the mirror faces south. Negative means it faces north. The question is simple yet tricky. What single fixed tilt angle maximizes the total beam energy intercepted over the entire day? Your first instinct might be to tilt it south, capturing that famous midday blaze. But wait, at this latitude on this special day, the sun at noon is perfectly perpendicular to a horizontal surface. If you tilt south, you actually reduce the midday punch while gaining in the morning and afternoon. Still, the sun spends a lot of time north of the east-west line, much more than you'd expect. Maybe a northward tilt is the real hack. This is where the maths enters the arena. You'll need to integrate the cosine of the incidence angle over all daylight hours, then find the tilt that makes that integral as large as possible. The key equations are waiting in your dusty field notebook. The cosine of the incidence angle equals the sine of the declination times the sine of latitude minus tilt, plus cosine declination times cosine of latitude minus tilt times the cosine of the hour angle. The sunrise hour angle itself depends on latitude and declination, given by the arc cosine of minus tan latitude times tan declination. For your location, that sunrise angle is a weird 100.9 degrees, or 1.76 radians. Because the sun rises north of east, the beam spends more time shining on a surface that leans north. When you crunch the derivative and set it to 0, the optimum condition boils down to a tasty little formula. The tangent of latitude minus optimal tilt equals the product of the sunrise hour angle and sine declination, divided by sine of the sunrise angle times cosine declination. Plug in all the numbers, and what do you get? The tangent works out to about 0.779, meaning latitude minus beta is roughly 37.9 degrees. Subtract that from 23.5 degrees latitude, and the optimal tilt pops out as negative 14.4 degrees. Yes, you heard it right. To go big on water points, you tilt your mirror towards the North Pole. It's completely counterintuitive until you see the daily path traced in the sky. The crowd in the viewing tent will gasp, your camel will nod knowingly, and the host will hand you the golden canteen. Now it's your turn.